In the beginning, compelling evidence for creation and the global flood. This is by Dr. Walt Brown, and we're going to be taking a look at the continental drift phase, and that's going to be on page 140 of the ninth edition that you can get at rsr.net, hpt.rsr.org. The continental drift phase. Material within the earth is compressed by overlaying rock. Rock's slight elasticity gives it spring-like characteristics. The deeper the rock, the more weight above, so the more tightly compressed the spring, all the way down to the center of the earth. The rupture path steadily widened during the flood phase. Eventually, the width was so great and so much of the surface weight had been removed that the compressed rock beneath the exposed floor of the subterranean chamber sprung upward. See 67F. Let's see, that's got to be 67F. Okay, right here. Okay, sprung upward. Let's take a look at that. It sprung upward. 67. Sprung upward. The birth of the Mid-Atlantic Ridge and the ultimate slippery slope. Ice is slick, especially if one is on ice skates, because as long as ice is directly under the great pressure of the metal blade, that ice normally turns to liquid water, so the ice skaters are actually sliding on liquid water. Imagine how fast a skater or a hydroplate would slide down a mountainside. Imagine how fast a skater or hydroplate would slide down a mountainside the size of the Mid-Atlantic Ridge, whose surface was 50 times slicker than liquid water. Supercritical water has a viscosity, frictional resistance, about 1/50th that of normal water. Supercritical water provided almost no resistance to the massive sliding hydroplates. It was much like riding on a cushion of air. Later in this book, we will calculate that speed. If you haven't studied figure 52 on page 127, the answer will surprise you. Contrast that with the century-old problem geologists have trying to understand how the rock in massive continental plates can scrape over and through mantle rock, which is solid, not liquid. Obviously, the plates cannot. Geologists have a serious problem. Okay. As the Mid-Atlantic Ridge began to rise, the gentle hydroplates started to slide downhill on the steepening slopes. This removed even more weight from what was to become the floor of the Atlantic Ocean. So the floor rose faster, the slopes increased, and the hydroplates accelerated, removing even more weight, etc. The entire Atlantic floor rapidly rose about 30 miles. When the first segment of the Mid-Atlantic Ridge began to rise, it helped lift adjacent portions of the chamber floor just enough for them to become unstable and spring forward. This process continued all along the rupture path, forming the mid-oceanic ridge. Also formed were fracture zones and the ridge's strange offsets at fracture zones. Soon afterward, magnetic anomalies, figure 50 on page 125, began to develop. The sliding hydroplates were almost perfectly lubricated by water still escaping from beneath them. Remember, the water trapped in sponge-like pockets in the chamber floor and ceiling was slowly squeezed out. See figure 57 on page 134. This sliding process resembles the following. A long train sits at one end of a very long level track. If we could somehow just barely lift the end of the track under the train, and the wheels were frictionless, the train would start rolling downhill. Then we could lift the end of the track even higher, causing the train to accelerate more. If this continued, the high-speed train would eventually crash into something. The long train of boxcars would suddenly decelerate, compress, crush, and jackknife. Continental plates accelerated away from the widening Atlantic. Recall that the rupture encircled the Earth, and the escaping subterranean water widened that rupture to an average of about 1,400 miles on both the Atlantic and Pacific sides of the Earth. Plates then slid away from the rising mid-Atlantic ridge and toward that 100-mile wide gap on the Pacific side of the Earth. The next chapter will explain why the Pacific floor simultaneously dropped as the Atlantic floor rose, furthering steepening the downhill slide and removing obstacles to the accelerating hydroplates. Eventually, the hydroplates ran into resistance of two types. The first happened as the water lubricated beneath each sliding plate was depleted. The second occurred when a plate collided with something. As massive hydroplates decelerated, it experienced a giant compression event, buckling, crushing, and thickening each plate and pushing up major mountains, many with fossils of sea life on top. To illustrate this extreme compression, imagine yourself in a car traveling 45 miles an hour. You gently step on the brake as you approach a stoplight and brace yourself by straightening and stiffening your arms against the steering wheel. You might feel 15 pounds of compressive force in each arm, similar to what you would feel lifting 15 pounds above your head with each hand. If we repeated this deceleration at the stoplight, but each time doubled your weight, the compression force in your arms would also double. After about 6 doublings each, especially if you were sitting on a lubricated surface, your arm bones would break. If your bones were made of steel, they would break after 9 doublings. If your arm bones were 1 foot in diameter and made of granite, 17 doublings would crush them. If decelerating mass was a hydroplate, the compressive forces would increase enough to crush and thicken the hydroplate and push up major mountain chains and create overthrusts in less than an hour. For more details, see key requirements for folding strata, buckling mountains, and overthrusting on page 214. Water could then drain off the thickened continents and into the newly opened and very deep ocean basins. Each cubic mile of land that rose out of the floodwaters, for each cubic mile of land that rose out of the floodwaters, 1 cubic of mile of floodwater drained. Here we go. Compressing a long, thin object, such as a yardstick, produces no bending or displacement until the compressive force reaches a critical amount. Once this threshold is exceeded, the yardstick or any long compressed beam or plate suddenly arches into a bowed position. Further compression bows it up even more. Buckling a hydroplate at one point also bends adjacent portions. Therefore, mountain chains were pushed up by the crushing of hydroplates. Where the compression exceeded the crushing strength of granite, the plates thickened and shortened. The collapse of strength in the crushed region increased the load on adjacent regions, causing them to crush, and the mountain chain to lengthen. Therefore, bending and crushing rapidly lifted mountain ranges. Naturally, the long axis of each buckled mountain was generally perpendicular to its hydroplate motion, that is, parallel to the portion of the mid-oceanic ridge from which it slid. So the Rockies, Appalachians, and Andes have a north-south orientation. Later sections of this book will explain why, in the years after the flood, melting deep inside the earth produced the earth's core and further vertical changes at the earth's surface. The forces acting during the dramatic event were not applied to stationary static continents resting on other rocks. The forces were dynamic, produced by rapidly decelerating hydroplates riding on lubricating water that had not yet escaped. As mountains buckled upward, water remaining under the plates tended to fill the voids formed. Some pooled water should still be in cracked and contorted layers of rock under mountains. This partially explains the reduced mass beneath mountains that gravity measurements have shown for over a century. Prediction number 2, beneath major mountains are large volumes of pooled salt water. Recent discoveries support this prediction, first published in 1980. The supercritical salt water appears to be below the Tibetan Plateau, which is bounded on the south by the largest mountain range on Earth. Prediction number 2, salty water frequently fills cracks in granite 5 to 10 miles below the Earth's surface, where surface water should not be able to penetrate. Note, each of the 59 predictions in this book is marked by an icon at the left representing figure 44 on page 118. Okay, friction at the base of skidding hydroplates below sinking mountains generated immense heat, enough to melt rock. Crushing produced similar effects as broken and extremely compressed blocks and particles slid past each other. The deeper the sliding, the greater the pressure pushing the sliding forces together, so the greater the frictional heat generated. Where heat was most intense, large volumes of rock melted. High-pressure magma squirted up through the cracks between broken blocks. Volcanic activity and floods of lava outpouring, called flood basalts, as seen on the Pacific floor and the Columbian and Deccan plateaus. In some regions, high temperatures and extreme pressure from the compression event formed metamorphic rock, such as marble and diamonds. The next chapter will explain the simultaneous production of deeper and far greater amounts of magma, some of which also escape to the Earth's surface as flood basalts. Wow. Okay. Some high-pressure subterranean water was quickly injected up into cracks in the crushed granite. This explains the concentrated salt water discovered in cracks 7.6 and 5.7 miles under Russia and Germany, respectively. Remember, surface water cannot seep deeper than 5 miles, implying that subsurface water was the source. This explains why the water's salt concentration in those cracks was about twice that of seawater, because that high concentration of subterranean salt water mixed during the flood with an approximately equal volume of pre-flood surface water, which had little dissolved salt. The new oceans gained most of their present salt. Because that high concentration of subterranean salt water mixed during the flood with an approximately equal volume of pre-flood surface water, the new oceans gained most of their present salt. As the mid-Atlantic ridge and Atlantic floor rose, mass had to shift within the Earth toward the Atlantic. Subsequent subsidence occurred on the opposite side of the Earth, especially in the Western Pacific, where a granite plate buckled downward, forming trenches. For details and evidence, see the origin of ocean trenches, earthquakes, and the Ring of Fire. Surrounding the Pacific is the Ring of Fire, containing the greatest concentration of earthquake and volcanic activity on Earth. On the floor of the Pacific and surrounded by the Ring of Fire are vast, thick lava flows and 40,000 volcanoes, each taller than 1 kilometer. Frictional heating caused by high-pressure movements under the Pacific floor generated these lava outpourings that covered the Pacific hydroplate. Therefore, the Western Pacific floor is littered with volcanic cones. Therefore, the Western Pacific floor is littered with volcanic cones composed of minerals typically found in granite and basalt. Continental crust has been discovered under the Pacific floor. See Note 51 on page 196, and the predictions on page 180.